in the rest of this lecture, our goal is to give some consequences of the Sylow theorems. We'll start with a corollary of the Sylow theorems that ends up being really useful. Let's say that G is a finite group and Q is a Sylow p-subgroup. Then Q is a normal subgroup in G if and only if the number of Sylow p-subgroups is 1. That is, Q is a normal Sylow p-subgroup exactly when Q is the only Sylow p-subgroup. So in general, when there's more than one Sylow p-subgroup, the Sylow p-subgroups are not normal. But in the case that a Sylow p-subgroup is the only one, that there's exactly one Sylow p-subgroup, then you know that it's normal. So this idea allows us to use some counting about Sylow p-subgroups to find particular kinds of normal subgroups in a group. So let's look at the proof. By Sylow 2, all of the Sylow p-subgroups are conjugate to each other. So what does it mean for there to be a unique one? That means that GQG inverse equals Q for all G in G. But that's exactly what it means for Q to be normal. So there's nothing deep going on here. You're just using the definition of what it means to be normal. Having a unique Sylow p-subgroup is the same thing as having a normal Sylow p-subgroup. All right, we'll see applications of that at the end of this lecture and then in the next. But first, let's see another type of application. Same setup as before. G is a finite group. NP equals 1 if and only if all of the subgroups generated by elements of p power order are p groups. So let me say that another way. NP equals 1 if and only if whenever you have a subset X in G such that the order of X is a power of p for any element little x in your set, then the subgroup generated by this subset X is a p group. OK, so we'll prove each direction. First, let's suppose that NP equals 1 and that X is a subset so that every element in X has p power order. So each element little x is contained in some Sylow p subgroup. Y, that was contained in the sort of stronger version of Sylow 1 that we proved, that every subgroup of order p to the I is contained in a Sylow p subgroup. So this element little x is certainly contained in the cyclic subgroup that it generates. So that's a subgroup of p power order. So it must be contained in a Sylow p subgroup. OK, so since NP equals 1, there's exactly one Sylow p subgroup Q. So that means every little x in X is contained in Q. So the set X is contained in Q. But that means that the smallest subgroup containing X is certainly contained in Q. So the subgroup generated by X is contained in Q. So what does that mean? Well, Q has order equal to p to some power. So any subgroup, like the subgroup generated by X, also has order equal to p to some power. So it's a p group. So that's the end of the proof of one direction. For the other direction, let's say that X is the union of all of the Sylow p subgroups. So what are we supposing for the other direction? We're supposing that whenever X is a subset of G so that all of the elements have p power order, the subgroup generated by X is a p group. So we're going to use this fact for a particular choice of a set X. And that set is going to be the union of all the Sylow p subgroups. Certainly, all of the elements in X have p power order. So by assumption, the subgroup generated by X is a p group. How big is that group? Well, if Q is a Sylow p subgroup, then Q is certainly contained in X because X is defined to be the union of all these things. So Q is contained in the subgroup generated by X. But now, this is a group of p power order, and so is Q. But Q, the order of Q, is the highest power of p dividing G. So this subgroup generated by X is at least as big as Q, but it can't actually be any bigger. So that means that Q is actually equal to the subgroup generated by X. That's true for any Sylow p subgroup. So that means that all of the Sylow p subgroups have to be the same because they're all equal to the subgroup generated by X. That proves that, in fact, there is a unique Sylow p subgroup so NP equals 1. So I'm going to pause and erase, and then we'll see some other applications of the Sylow theorems. We'll next prove a result about how the Sylow p-subgroups and Sylow q-subgroups relate to each other in a special case. So let's suppose that p and q are distinct primes dividing the order of G, and that NP equals NQ equals 1. So there's a unique Sylow p-subgroup and a unique Sylow q-subgroup. And we just saw from the result from the beginning of this video that that unique Sylow p-subgroup is normal, and that unique Sylow q-subgroup is normal. The statement we're going to prove is that the elements of the Sylow p-subgroup of G and the elements of the Sylow q-subgroup of G commute with each other. So I just want to be clear that we're not claiming that either the Sylow p-subgroup or the Sylow q-subgroup are abelian. But what we are going to show is that if you take something in the Sylow p-subgroup and something in the Sylow q-subgroup, then they commute with each other. So let's name these groups. Let's say that P is the Sylow p-subgroup of G and Q is the Sylow q-subgroup of G. So the first idea is to consider the intersection. So the intersection is a subgroup of P and it's a subgroup of Q. So Lagrange's theorem says that the order of the intersection divides the order of P and divides the order of Q. So in particular, it divides the greatest common divisor of the order of P and the order of Q. But because these are Sylow subgroups, P has order P to some power and Q has order Q to some power, so their GCD is 1. So that means that the intersection is the trivial subgroup. So that's a big part of the argument. Now what we're going to do is take some element of P and some element of Q, and we're going to show that xy equals yx by showing that xy x inverse y inverse is in the intersection of P and Q. So what does that do for us? Well, okay, xy x inverse y inverse. If that's the identity, then these elements commute. So that's an if and only if statement. So once we know that xy x inverse y inverse is in the intersection of P and Q, then we know that that product is equal to 1 because the only thing in the intersection of P and Q is the identity element. All right, so let's show that xy x inverse y inverse is in P, and also that xy x inverse y inverse is in Q. So first, let's take this product and just group the terms together as xy x inverse times y inverse. Y inverse is in Q for sure. And then xy x inverse is also in Q. Because there's a unique Sylow q subgroup, it's normal, which means that if you conjugate by any element in G, you stay in that subgroup. So in particular, xy x inverse is still in the subgroup Q. So we get something in Q times something in Q. So this product is in Q. OK, so why is that product also in P? We have a different way to group the product of these 4 terms. We can write it as x times y x inverse y inverse. So this is the conjugate of the element x inverse by the element y. And it's the same idea exactly. The Sylow p subgroup P is normal in G. So that means you conjugate any element inside P by any element of G, and you stay in that subgroup P. So x inverse is in P, y x inverse, y inverse also stays somewhere in P. So we have something in P times something in P. So this product is in P. So now that we see that it's in Q and it's in P, that means that this product is trivial. So these elements commute.